What we need to understand is at a very basic level how the cells are being governed by their environment and how we can in turn engineer the environment of the cells to affect an outcome that we want. So there's got to be a very basic marriage of biology and engineering to go from the molecular level up to a device level that would go into patients. We work with an orthopedic surgeon at the Cleveland Clinic, Dr. George Mushler, and he treats a lot of patients who get big tumors in their bones. And so they have to cut out very large segments of bone. And right now there isn't a very good replacement for the large defects that are taken out. So right now patients go in and have their knee joint chopped off and a prosthetic replaced. You can make a prosthetic knee, in fact a metal knee, with this mold that was made by three-dimensional printing about 10 years ago. But what we want to do is instead of chopping the knee off and replacing it, we actually want to regrow the damaged tissue. So now we're using three-dimensional printing to build very sophisticated scaffolds that give instructions to the cells on how to regrow bone. With the three-dimensional printing process, we build complicated objects as a series of very thin two-dimensional slices. We start by spreading a powder into a very thin layer, about 100 microns thick. This particular powder is made out of a biodegradable surgical polymer. Then we put a stencil over the top that governs where liquid can be printed onto this layer. Then a print head rasters across the surface and prints very, very fine, tiny droplets of a liquid, in this case chloroform, to dissolve the particles of powder and bind them together. We can also add lots of other things that might be growth factors or things that would mediate the biological response during this process. In this particular build, we have 77 different layers. At the end, what we have is a scaffold for bone regeneration. And we're in the stage right now where we're testing these scaffolds in a dog model with an orthopedic surgeon who's developing better ways to use marrow in his human patients. The scaffold has a very, very precise internal architecture. So we have a design that lets us put the marrow in and have it go to very specific places. We also can use the design to call blood vessels in from the surrounding tissue. So there was an enormous amount of engineering that went into making a three-dimensional model before we ever turned on the three-dimensional printer. And we started with thinking about how the bone will grow into this scaffold. We're at a very exciting time in the science of biology. You read about it almost every day in the newspaper, the Human Genome Project, proteomics, things that make the front page, make the business page. But what it takes to translate discoveries in basic science, including biology, into things that people use is engineering. So you have to be able to go from molecular to a systems level and understand a huge context of length scales and time scales. You require engineering. At the same time, to move a science forward, you need new engineering tools and new ways of engineering analysis in that field. And we're at a very exciting time because engineering is starting to both create products out of biology and feed back into biology to make post-genomic biology a much more pervasive and exciting discipline. So MIT is really the center of the universe where this is happening.